Okay, so thank you very much, Mason, for having accepted our invite, and thank you very much, all of you, for being here today. So this is our first external guest of this new round of TeDCog sessions for this year, and I'm honored to present to Dr. Mason Youngblood. He works as a postdoctoral fellow at Stony Brook University at the Institute of Advanced, I have it here, Advanced Computational Science, right? And his work focuses on the relationship between cognitive bias and behavior and belief evolution. And he combines cognitive science, computational social science, and cultural evolution. So I guess that today he will be talking about a recent paper that he published together with other authors in humanities and social science communications, right? Am I right? Okay, so whose title is the title of this presentation? And so I will leave it to you, Mason. The floor is yours.
Thank you very much for the introduction. Just a quick heads up that I have a speech impediment that will pop up periodically. Thanks again for the invitation. I'm going to be talking about a project that we just recently published on the role that we think cultural transmission bias played in the spread of the voter fraud conspiracy theory on Twitter during the most recent presidential election in the US. And if you're interested in more details, there is a QR code and link here that takes you to the paper, and the paper includes a link to our GitHub repository that has an R-packaged version of our model, as well as our pre-registration document of our model. So first, I'm going to start off with a quick overview of the cultural evolution framework and what I mean by transmission biases, and the kinds of methods that we can use to detect them. I'll then go over this study, and then at the end talk about a few of the limitations and what we can do to correct them. So first off, what is cultural evolution? So I like to define cultural evolution as change in the socially learned information of a population over time. And in this framework, the inheritance mechanism, in quotes, of cultural evolution is cultural transmission, which I consider to be interchangeable with social learning. So after over the last few decades, the field of cultural evolution has uncovered a great deal about how processes of cultural transmission at the level of individuals, shown here on the left, scale up to influence patterns in the spread of ideas and behaviors over time, such as in this example on the right of the spread of Austronesian languages over time. So these kinds of cultural evolutionary approaches can be very useful in cases like conspiracy theories, where we're interested in understanding how the cognitive biases of individuals influence the spread of information. So I mentioned cultural transmission. So of course, transmission in social learning is not completely random. We have a large set of biases that cause us to adopt some behaviors and ideas over others, and also transform the information as it's being adopted. And these three forms of transmission bias are often viewed as the most important in the field of cultural evolution. So content bias, frequency bias, and demonstrator bias all affect the probability that a behavior is adopted, but they are based on different cues. So a content bias is when the inherent characteristics of a cultural variant or a behavior or idea affect its probability of adoption. In the context of social media, people may be more likely to share messages that are more positive or more negative in their emotional valence. And then a frequency bias, which includes conformity bias and an anti-conformity bias, is when the frequency of a variant in the population disproportionately affects its probability of adoption. So if a behavior or idea is extremely rare or extremely common, it might be more likely to be shared. And of course, in humans, we know that people tend to be conformist in many contexts, but not all contexts. And then finally, a demonstrator bias is when some characteristics of the individuals expressing a behavior or idea affect its probability of adoption. And there is some evidence in humans that people are more likely to adopt behaviors and ideas expressed by celebrities or other prestigious figures. Oh, by the way, feel free to interrupt me at any point. Just unmute your mic and start talking if you have questions during the talk. I'm completely happy to answer as I go, clarify. So all three of these factors probably influence information spread on social media. But it is important to note that the third, a demonstrator bias, is very hard to distinguish from the effects of network structure. So basically, a demonstrator bias online would very likely be targeted towards something like follower count, or whether an account has been verified, at least before X's new policy of paid verification. So a positive effect of these factors on the spread of information would be extremely difficult to differentiate from the fact that individuals with larger platforms will already have greater reach under neutral conditions. And this is particularly hard when we don't have access to the internal details of recommendation algorithms. So in this project, we will refer to the combined effect of demonstrator bias and network structure as follower influence. And we'll focus our attention on these first two, so content bias and frequency bias. Frequency bias is also confounded a bit, which we can talk about more after I start going through our model. So we have these biases that affect the probability that we adopt certain behaviors or ideas. How can we detect evidence for these in large cultural corpora? Well, it turns out that these different forms of bias change the distribution of cultural variance in the population. So this plot here has the identity of tweets on the x-axis, and their retweet frequency, how many times they've been retweeted on the y-axis. And both axes have been log transformed here. And you can see that these four different conditions, which are just different parameter values in our model, lead to different shapes in the retweet frequency distribution. Excuse me. So green and blue are the most obvious. And green here is incorrectly labeled. It should be an anti-conformity bias. So this blue line is a conformity bias. So when people are more likely to share messages that have already been heavily shared by other individuals. And then the anti-conformity bias in green is the opposite. And you can see that these two biases have predictable impacts on the retweet frequency distribution. So when there's a conformity bias, the more common messages get a boost compared with the less common ones. And then under anti-conformity, it's the opposite. The less common ones get a boost. And then a content bias and follower influence, which is a demonstrator bias and a network structure, also lead to differences. So it's clear that when these transmission biases play out in populations, they lead to statistical patterns that are very clear. So how do we embed this into an inference framework?
Sorry, Mason, can I ask a quick question at this point? What does the x-axis on this graph show us? Is this, perhaps I haven't quite understood this graph, is this the number of tweets that have been tweeted by a particular individual, or?
No, it's not. So yeah, it's a bit confusing, this axis label. The x-axis here is types, where a type is an individual tweet, and then the y-axis here is tokens. So how many times that individual tweet has been retweeted. So here, tweet one is just the most heavily retweeted tweet, and these are just ranked.
I understand.
In order.
Thank you.
Yeah. So to do inference based on this effect, I use a framework called generative inference, which was very nicely reviewed by Anna Candler and Adam Powell a few years ago in Philosophical Transactions. And the basic idea of generative inference is to simulate a bunch of data from a generative model of your system, usually an agent-based model, and then to find out what combination of parameter values of your model best recreate your observed data. And that process of parameter fitting is usually done with some form of approximate Bayesian computation. And I'll describe how I prefer to do that in more detail in a few slides. So first, just a quick review. Agent-based models are models that are used to simulate interactions between individual people. So in agent-based models, unlike mathematical models, we have these individual nodes in our model that denote people, and those people can transfer information with one another according to a set of rules. And we try to design our agent-based models to reflect reality as closely as we possibly can, but of course, we always have to make a lot of simplifying assumptions. And these models often include things like population structure, a set of rules that govern how the agents interact with one another, and parameters that control the kinds of information that agents are most likely to pay attention to. So in generative inference, we have this agent-based model. We simulate a bunch of output from that agent-based model, where for each individual run of your model, you know the starting parameters and the shape of the output that it generates. And then step two, at least how I prefer to do it, is you train a machine learning classifier to predict the starting parameters of your model from the shape of the simulated data that it generates. And I like using random forest for this process because it combines predictive power with interpretability. It's much less of a black box than a more sophisticated methods like deep learning. And then you provide the trained classifier with your observed data, and you ask it to predict what parameter values of the model probably generated your observed data.
Sorry to interrupt, Mason. I have a question from Luke.
Hello. Just a quick question. What is the error rate of the machine learning in determining the input parameters based on the output?
Yes. So it is calculated. It can be calculated just by having training data and then testing the accuracy of your classifier on test data. So of course it will be different for every model that you use and every system that you use. In this case, I'm constructing posterior distributions for all of the parameters that include the error and prediction.
So, Mason, can I add another comment or question? So just to make sure.
Of course.
So effectively, what you're starting out with here is a parameter recovery exercise because
exactly.
Right. With the simulated output, you know what you put in to simulate the output.
Exactly.
The reason you trained the machine to tell you what it was is so that you can then apply that to observed data where you don't know.
Exactly.
Okay. So the idea then is that you look at something in the wild and the machine spits out, oops, this much content bias, that much frequency, etc.
Exactly.
Is that the objective? Okay, thank you.
That's exactly right. And I should mention that usually like in standard statistical models, you don't need to have this step two because you have a likelihood function that basically maps the parameters of your equation-based model to the output that it generates. But in cases like this, where we have a complex custom agent-based model that does not have a likelihood function that can be computed, that's why we have to have this step two of training a classifier to do it for us. And basically what the classifier is doing is approximating a likelihood function. So this kind of method has been used quite heavily in the last 5 years in the field of cultural evolution by myself and others to investigate the influence of transmission biases in a variety of systems, such as pottery, traditions, and archaeology, writing systems and language. and even birdsong and music. So it is becoming a more widely used method in the field of cultural evolution, but the approach actually comes from ecology. So I should mention up front that this is not the first time that this approach has been used for social media. The first time it was used by Carignan et al. On a big data set of true and false headlines from Twitter, and they found that the spread of the headlines was more consistent with random copying than it was with conformity. But their model did not include parameters for follower influence, that combination of a demonstrator bias with network structure, and also did not explore the influence of a content bias due to computational limitations. So here I combined aspects of this model by Carignan et al. With a more general model that I recently used to investigate the cultural evolution of birdsong, that includes content bias, frequency bias, and demonstrator bias or network structure, all in one package. All right. So now that I've introduced the approach, I will talk about the actual research model. So in this case, we were interested in applying this approach to the spread of the voter fraud conspiracy theory during the 2020 US presidential election. And this conspiracy theory is the idea that the election was compromised by widespread and coordinated voter fraud. And it was, of course, shared online by major political figures, including our former president, despite the fact that officials within his own administration from several different departments investigated it and concluded that there was no evidence for it, and that the 2020 election was actually the most secure in American history. But unfortunately, polls from a year after the election indicate that at that point, up to a third of the American public and a majority of Republicans believed that the election was compromised by widespread and coordinated voter fraud. And so this conspiracy, of course, culminated in the storming of the Capitol on January 6th. And after this event, Twitter ended up suspending President Trump and 70,000 QAnon-affiliated accounts due to incitement of violence. And I mention that because all of our data was collected in real time. So it includes all of those accounts that were suspended after the storming of the Capitol. So given the scale and the impact of this conspiracy theory, it's very important for us to understand why it spread online. And to bring it back to transmission biases, we were particularly interested in if the spread of it online was caused by or boosted by either a content bias, causing people to share information that has a particular form of content, or a frequency bias, such as conformity, after accounting for the effect of a network structure and a demonstrator bias if it is at play. So what was our data? So our data was collected by Anton Abalov and his team at Cornell Tech here in New York. And they have a website for their data of voter fraud, 2020.io. It's a great data set. I highly recommend checking it out. It was collected in real time between the 23rd of October and the 16th of December in 2020. And they basically iteratively expanded a set of search terms starting from voter fraud and hashtag voter fraud based on commonly co-occurring terms. And they did an analysis to conclude that they got approximately 60% of tweets related to voter fraud on the platform during this time period. They did an analysis of retweets and identified clusters of users in this data set who were retweeting each other a lot. And because of the fact that we were interested in cultural transmission rather than just general debate and discourse, we focused on this population highlighted in yellow that really only retweets among themselves and has 83% of users with QAnon hashtags in their bios. And the rate of QAnon hashtags in their bios was 5 times to 100 times higher than in the other clusters. So basically, we focused our analysis on the hardcore conspiracy theorists in this data set so that we are looking at patterns of information spread as opposed to just debate about the conspiracy theories. An important thing to note here is that we were interested in patterns of retweeting, and there's also patterns of quote tweeting as well. So for the purpose of constructing the distribution of retweets, we treated all of the quote tweets as if they were new tweets. And this is because quote tweets, like new tweets, have their own text and can themselves be retweeted. And we did this both with the actual data and with our agent-based model. All right. And then I promise I'm getting to the agent-based model soon, but there are a couple of major confounds that I should highlight up front because they're important for the interpretation of our model. So the first is that when we built this model and pre-registered this study, there were basically no details about the timeline algorithm online. And even though Twitter recently open-sourced their algorithm, open-sourced in huge quotation marks, they did not provide any of the training data that's needed to actually use it. So we still aren't able to run simulations from their algorithm to see how it boosts different kinds of information. That being said, their GitHub repository does list all of the features that their deep neural network uses for ranking tweets. And it primarily uses information about engagement metrics and aspects of the tweet author. And this means that the effect of the algorithm is going to confound the results for frequency bias and follower influence primarily. The algorithm does not use information about, high-level metrics of the actual content of tweets, like the emotional valence. So it's not as confounding for our effects of content bias. and then the other confound is that we did not have access to the actual network structure of which users follow who. But again, we don't know how the algorithm actually weights the importance of network structure. And people searching for conspiracy theories online often use the keyword search function as well. So we just use a parameter in our model to approximate the influence of network structure, as opposed to having an explicit network structure in our model. So with those two caveats, here is how our model works. So we had a fully connected population of about 350,000 users, where each user is matched up to a real person in the Twitter data, where each real person has a unique follower account, activity level on the platform in each time step, and an overall probability of tweeting and original tweet versus retweeting an existing tweet. So each user has an individual value for each of these. And in this way, we retain the internal correlations between these things. So because different users have different strategies. Some people have very few followers and just post a lot of retweets, and other people have huge platforms and only tweet original content at a very low rate. And it's important to account for those things. So we then initialize this model with retweet frequencies sampled with replacement from the first time step in the real data. And then we run this model over time, where each time step corresponds to a 6-hour interval in the actual data set. If individuals retweet a new tweet, well, at the start of each time step, a pseudo-random subset of users becomes active and tweets based on the real observed activity in that time step. And the active users in a given time step either tweet an original tweet with their probability mu, or retweet an existing tweet with the inverse of mu. And mu is computed from the actual data. It's the proportion of that user's original tweets to retweets in the data. And each new original tweet is assigned an attractiveness index, which is meant to be agnostic to the actual target of attractiveness. It's just an index. We just assume that the attractiveness of tweets in terms of content fits a normal distribution with a mean and standard deviation of 1 and a bound at 0. And then if users if they retweet as opposed to posting an original tweet, then the probability of basically we compile a table of all of the tweets that currently exist in the population, and then we compute a probability of retweeting each of those tweets, where that probability is based on a set of cues. So the frequency of the tweet, how many times it's already been shared, f of x. P of x is the number of the author's followers. M of x is the attractiveness of the tweet, the attractiveness of its content. And then the age, to just reflect the fact that as tweets become older, they are less likely to appear on people's timelines. And then we raise each of these to a parameter that controls the impact that that Q has on the probability calculation. So for alpha, positive values increase the influence of frequency. I'm going to gloss over the details for time here. And yeah, positive values of each of these increase the influence that they have on the probability function. And so these four exponents are really what we were interested in estimating with approximate Bayesian computation, because these are the things that correspond to those transmission biases. So we have these four target parameters, and what we do is we run our agent-based model 500,000 times across a wide range of combinations of these parameter values, and we generate a bunch of data, and we compute summary statistics from that data that act as the inputs to our machine learning classifier. In this case, we trained a random forest of 1,000 trees to predict the input parameters from the output summary statistics. And then we expose that trained classifier to the actual data, and we ask it what probably generated it. Here are the posterior distributions for each of the parameters. The results are kind of messy, but that's okay. So I'll highlight a couple of things first before talking about our main effective content bias. So first, follower influence and frequency bias here seem to be slightly bimodal. And while it's possible that these smaller peaks may correspond to alternate parameter combinations that partly reproduce our real data, we ran our analysis with different forms of approximate Bayesian computation besides random forest. And we found that these peaks aren't always there. And in those cases, the posteriors just converge towards small values around 0. So in general, for these parameters, we're mainly interpreting these global optima on near 0. And then for age dependency, the posterior is kind of noisy and has signal across the entire prior, which is this dotted line here. And so we aren't really interpreting the results for age dependency because the error rate is just so high. So with that, let's focus on the global optima for these two, and then for our clear signal of content bias. So the posterior distribution for content bias is around 4.6, which is a value that causes a tweet that is one standard deviation above average in terms of the attractiveness of its content to be 24 times more likely to be retweeted. So it's a very strong effect of content bias. And this indicates that there is probably a strong effect of content at play in the patterns of retweeting. But follower influence and frequency bias both are converging towards 0. For follower influence, this indicates that if there is a demonstrator bias and if there is an impact of network structure, that it's relatively weak compared with other factors. And then the effect of frequency bias is a bit complex because in standard cultural transmission models, an effect of 1, where the probability of information being shared is perfectly proportional to its frequency, is usually viewed as neutrality. But in this case, that may not be the case because that assumes that everyone sees information in a completely neutral way, and the algorithm makes that not true by by default. So if you're interested in the interpretation of this, I recommend checking out the paper. But in terms of time, I should just move on. So we found this strong effect of content bias, and the next step was figuring out what aspect of the tweets this content bias was targeted towards. And to do this, we conducted sentiment analysis with this model called Vader. Because at the time we did not have access to ChatGPT, which is now the cutting edge in this. But what's great about Vader is it's trained with data from social media that includes emojis and URLs and all of that. And it actually outcompetes it outcompetes individual human raters when used with previously analyzed data sets, which is great. So we analyzed our whole data set with this, and then we did a whole process of constructing a best fitting model where we iteratively added parameters to a general linear mixed model. We saw what parameters improved model fit. And then we ended up with this final model where we were predicting retweet count, including user as a varying intercept, and then including how long the tweets are, if the tweets contain media or not, what the follower count of users is. And then we checked out the different output of sentiment analysis, and we found that the compound score, which includes information about the direction, positive or negative of emotional valence, and the strength in our model, improved fit best. And we found that the compound score had a significant impact on retweet count in the negative direction. So tweets that have a greater amount of negative sentiment are more likely to be retweeted. So in summary, we are concluding that that content bias that we detected with the agent-based modeling and approximate Bayesian computation is targeted towards negative emotion that we detected using the general linear model. And we think that there is either an extreme novelty bias or irrelevance of frequency information, which I didn't talk about much here, but you can check out more details in the paper, or we can discuss now. And in general, we're most confident in concluding that that these results show a content bias for negative emotion helped drive the spread of these claims. And of course, a content bias for negative emotion online is not a controversial claim. Our results here are consistent with previous work that shows that emotionally negative content has an advantage across a variety of domains, including fake news articles, coverage of climate change, and political events. Although the direction of emotion can be different depending on the information that's being spread. So there is probably variation across domains and also individuals. So messages about same-sex marriage, for example, are more likely to be retweeted if they contain positive language, whereas messages about climate change are more likely to be retweeted if they contain negative language. So it seems like conspiracy theories fall into the latter category. And then just a concluding thought for our discussion. My biggest takeaway from this project is just how challenging it was to deal with the fact that we don't have access to Twitter's timeline algorithm, and that we don't have access to the actual network structure of users. And this made it very difficult to construct a realistic null model of behavior online. And I think that these kinds of realistic null models are sorely needed in our field. So there are a couple of new papers proposing more complex models that include different forms of recommendation algorithms that would allow us to simulate how different kinds of recommendation might interact with these kinds of biases online, but we still need real data from real platforms in order to tune those models to what's happening in cases of information spread online. So with that, I would be happy to answer any questions you have. And if you're interested in checking out the paper, here again is a link in QR code.
So thank you very much, Mason. And also thank you very much for leaving enough time for questions. We already have one from Dawn. So please, Dawn.
Hi, thanks, Mason. That was a great talk. I was actually very curious about the data set you used, and because what we know on Twitter is that sometimes you have a lot of bots that enter it and specifically retweet them. So my question is, did you have to handle these in the data set, and if so, how?
Yes, that's a great question. And the answer is we were not able to handle that. But what's interesting about the way we constructed our model, because of the fact that we based the behavior of agents in our model on the behavior of the actual users, then that means that our agent-based model includes the behavior of the bots in our data set. So we kind of indirectly accounted for it that way by having an agent-based model that includes bot-like behavior among a subset of the agents.
Well, I guess an interesting question. I mean, I don't know whether it's even possible to distinguish the bots, which is always the sticking point, is how much is the behavior and the patterns that you then find being driven by the bots as opposed to actual human behavior. That would be really cool if you could answer it, but I know it's probably very tough.
It would be, yeah. And I think it would be really interesting if you're able to detect signatures of real human cognitive biases from the behavior of a bot in order to detect bots on the platform. But I don't know of anybody doing that, actually.
Yeah, thank you.
Can I ask a question about the fascinating finding that follower count and didn't seem to have much of an effect, at least in your agent-based model. And to me, that's sort of unexpected.
Yes.
Can you comment on that some more? I mean, what do you think is going on there?
Yes. So I think a part of that is the fact that we focused on the most hardcore conspiracy theory users, that cluster of users in yellow here, that are people with QAnon hashtags in their bios. I think this is a subset of more fringe users on the platform. And so our distribution of follower counts that we used for our agent-based model based on the users we included was extremely skewed. There were only a few users that had very high follower counts. And so I suspect if you ran this kind of analysis with a more general population of users, you would find a much stronger effect of follower count.
Okay.
We have a question for Luke, from Luke.
Hello, yes. So the agent-based model, is it transferable to other social media networks, or is it only built for Twitter? Because as the internet becomes more and more divided with extreme positions taking place on other social media sites, such as Rumble and Telegram, how can this model potentially be transferred to other social media sites in order to get a fuller picture of the biases at play?
Yes, that's a great question. So in its current form, as an R package, our model is very much, it like requires a standardized input that is specific to Twitter. But what that input includes is just the identity of users, their follower account, their activity over time, etc. And so in theory, it could be used for other platforms. And it's I should also mention that this paper has been in the publication pipeline for a couple of years. And so it was very frustrating for me as an author to, by the time this paper came out, the platform that it's about was basically in the process of imploding. So yeah, at this point, I think more general models are very needed. But I can, there's a really exciting new preprint I recently found that proposes a more general model that includes different forms of recommendation, as well as it has an opinion dynamics model embedded into it. And I think these kinds of approaches that are more agnostic to the platform and just include extremely general forms of recommendation algorithm are probably the best way to go.
Brilliant. Thank you very much. I'll give that a look over.
We do have time for a few brief questions. I don't know if we have any. Otherwise, I do have a question, Mason. So I think you commented this at the end of your presentation. So do you think this kind of effect does replicate with other kind of conspiracy theories, like, I don't know, vaccines or stuff like that? Because I think you mentioned like same-sex marriage, churns into different kind of emotions, so goes towards positivity values. So what about other kind of conspiracy theories?
Yeah, and in particular, health-based conspiracy theories are where I'm most interested in exploring it next. I'm working with a nonprofit that focuses on fighting health-based misinformation, and so we're planning basically a follow-up to this study about different forms of health-based misinformation, both political, like in the US, vaccines and abortion, and apolitical, like statins and other drugs. There are a lot of less politicized conspiracy theories online about those. And we don't have any results yet, but we should in the next year or so. But I know that there are a couple of papers that have evidence for strong negativity bias and anti-vax communities online. So, but I'm skeptical of whether that extends to all health-based conspiracy theories or just those that are really politicized and kind of couched in culture war framework, like voter fraud is.
I see. I don't know if we have any other questions. Otherwise, I do also have another meeting now in, in 5 minutes. So if we don't have any other question, I would like to thank you again, Mason, for being here today, and thank you everyone for attending. And well, I'll see you next week. And yeah, that's it. So have a nice weekend, all you. Bye bye.
Thanks again for having me.
Thank you.